Hello everyone, this is audio recording for visually impaired students from Modern Inorganic Chemistry. Let's start chapter non-aqueous solvents. Most of the chemical reactions are carried out in solutions and the behavior of substances also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification, together with its favorable physical and chemical properties such as long liquid range 0 to 100 degrees Celsius, high dielectric constant 78.5, specific heat, heat of voltization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying out chemical reactions are called non-aqueous solvents. Attempts have been made to find some other substances which could behave as good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid NH3, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important features of non-aqueous solvents such as NH3 and SO2. Physical properties of solvent and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reactions and separate the products more conventionally. Some of the important physical properties of the solvent are discussed below. Number 1. Melting point and boiling point, liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reactions in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvents are given in table 1. Solvent H2O melting point 0.0, boiling point 100. NH3 melting point minus 77.7, boiling point minus 33.4. HF melting point minus 89.3, boiling point 19.5. SO2 melting point minus 75.5, boiling point minus 10.2. CS3COOH melting point 16.6, boiling point 118.1. Solvent HCO and CS3 whole twice TMF melting point minus 61.0, boiling point 153.0. H2SO4 melting point 10.4, boiling point 300. With decomposition, it is clear from the above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperature, while NH3 and SO2 can act as solvents only at low temperatures. Number 2. Heat of fusion and heat of vaporization. The value of heat of fusion and heat of vaporization helps to know the nature and strength of forces which hold the molecules of the solvents together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitudes of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of the intermolecular forces, and these also determine the solvent properties. A better idea of the intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Troton constant, that is delta H evaporation upon Tb is equal to Troton constant. For normal liquids, if molar heats of vaporization are expressed in calorie and boiling point in absolute scale 0 Kelvin, then the Troton constant has the value 21.5. If delta H evaporation are in joules, Troton constant is about 90 for normal liquids. Such liquids exist as independent molecules without any bond between them. A higher value of Troton constant indicates associated molecules. For example, common solvents like water, ammonia, hydrogen fluoride have Troton constant value greater than 21.5 and are therefore associated liquids. The molecules of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged ends of the molecules come near to each other. The molar heat of fusion of vaporization of some solvents are given in table 2. Solvent water, molar heat of fusion kilojoule per mole 6, molar heat of vaporization in kilojoule per mole is 40.65. Ammonia 5, molar heat of fusion 5.65 kilojoule per mole and molar heat of vaporization 23.56 kilojoule per mole. Sulfur dioxide, molar heat of fusion 7.40 kilojoule per mole and molar heat of vaporization 24.94 kilojoule per mole. Hydrogen fluoride, molar heat of fusion 4.58 kilojoule per mole, molar heat of vaporization 30.26 kilojoule per mole. The inspection of table 2 shows that the values of molar heat of fusion for water and ammonia are almost same. This means that forces which hold molecules together in water and ammonia are of same magnitude. Number 3. Dielectric constant. This property is a measure of the polar nature of the solvents and helps to estimate the solubility of polar or non-polar substances in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equals to Q positive Q negative upon epsilon naught R square, where Q positive and Q negative are the charges of the cation and anion respectively. R is the distance between them equal to the radii of the ions. Epsilon is the constant called the dielectric constant of the solvent. If epsilon is large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions and hence it will be easy to dissolve an ionic substance. Thus, in solvents of high dielectric constant, the ionic substances will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. The dielectric constant of some common solvents are given in table 3. H2O 81.7 at 18 degrees Celsius, NH3 22 at minus 33.5 degrees Celsius, SO3 17.3 at minus 16 degrees Celsius, CS3COOH 9.7 at 18 degrees Celsius, HF 83.6 at 0 degrees Celsius, HCN 123 at 16 degrees Celsius, TMF 36.7 at 25 degrees Celsius, H2SO4 100 at 25 degrees Celsius. It is clear that solvents like HF and H2 are good solvents for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvents like NH3 and SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compounds, and especially those containing multi-charged ions. For example, carbonates, sulfates and phosphates are practically insoluble in liquid ammonia or liquid sulfur dioxide. Number 4. Dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecules. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moments have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity results in strong bond between the solvent and the solute molecules and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and helps in dissolving the solute. Number 5, viscosity. It is a measure of the fluidity of the solvent. Solvents like water, ethyl alcohol, and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rates at ordinary conditions. In solvents of low viscosities, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increasing the viscosity of a liquid, increase the difficulty of such operations. Types of solvents. Non-aqueous solvents have been classified in many ways. The following are the important classifications based upon the chemical properties of the solvent. Number 1, protonic and non-protonic solvents. Number 2, acidic, basic or amphiprotic solvents. Number 3, ionizing and non-ionizing solvents. Number 4, coordinating and non-coordinating solvents. Protonic and non-protonic solvents. The solvents from which protons can be derived are called protonic or protic solvents. Therefore, protonic solvents contain ionizable hydrogen. Common examples are H2HF, H2SO4, HCl. The solvents from which protons cannot be ordinarily derived are called non-protic solvents. These are also called aprotic solvents. In other words, these solvents do not contain ionizable hydrogen atom. Common examples are liquid SO2, N2O4, C6H6, CHCl3, CCl4. Number 2, acidic, basic or amphiprotic solvents. This classification is based upon the acidic or basic behavior of solvents. The solvents which have a strong tendency to donate protons are acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride and acetic acid, etc. Solvents which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvents. For example, liquid ammonia, pyridine, hydrazine, ethylene diamine. The solvents which neither have a strong tendency to gain nor a strong tendency to lose protons are called amphiprotic or amphoteric solvents. In other words, they neither behave as strong acidic nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Number 3, ionizing and non-ionizing solvents. The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some common examples are H2NS3, HF, SO2, N2O4, ClF3, BrF3, POCl3, etc. These ionize as shown below. These solvents are generally polar or ionic in nature. On the other hand, these solvents which do not ionize at all are all non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar or non-ionic in nature. Number 4, coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, NH3SO2, dimethyl sulfoxide, acetonitrile, dimethyl formamide, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvents. For example, CCl4, saturated hydrocarbons, etc. These are not of much interest to organic chemists. Type of reactions in non-aqueous solvents. The following types of reactions commonly occur in non-aqueous solvents. Number 1, metathetical or precipitation reactions. The reactions in which precipitation occurs on mixing two solutions are called metathetical or precipitation reactions. These type of reactions can be predicted if the values of the solubility products of the compounds formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. 2AgNO3 plus BaCl2 on adding water gives 2AgCl pipette plus BaNO3 whole twice. On the other hand, in liquid ammonia, a precipitate of silver chloride combines with the barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. 2AgCl plus BaNO3 twice on liquid NH3 BaCl2 pipette plus 2AgNO3. Therefore, reversal of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water-soluble copper sulfate may be precipitated in anhydrous acetic acid. Number 2. Salt formation. The reactions between appropriate acidic and basic substances to form salts are called salt formation reactions. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium Urite cannot be prepared by the reactions of urea on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water, and uride ion will take a proton from water to form hydroxide ion. Na positive NHCO NH2 negative plus H2O gives Na positive OH negative plus NH2CO NH2, that is urea. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. NH2CONH2 plus NaNH2 on liquid NH3 gives Na positive NHCONH2 negative plus NH3. Number 3. Acid-base reactions. The acid-base reactions in non-aqueous solvents can be explained on the basis of solvent system concept. As already learnt, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristics of the solvent. Similarly, a base is a substance that gives the anion characteristics of the solvent. The acid-base behavior of a substance depends upon the acid-base nature of the solvent, the character of the solute, and the solute-solvent interactions. In the case of protonic solvents, cation is the solvated proton, and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ion act as acids and NH2 negative ions act as base. The neutralization reaction is NH4Cl plus NaNH2 on adding liquid NH3 gives NaCl plus 2NH3. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis acid-base type of reactions can occur because of non-ionization of the solvents. The acid-base behavior of a solute in a solvent depend upon the acidity or basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. CH3COOH plus NH3 gives CH3COO negative plus NH4 positive, and this is in equilibrium state. CH3COOH plus H2O equilibrium state, CH3COO negative plus H3O positive. CH3COOH plus H2SO4 in equilibrium state with CH3COOH2 positive, HSO4 negative. Number 4. Solvolytic reactions or solvolysis. The reactions in which the solvent molecules react with the solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute. Molecular ion are called solvolytic reactions. Since these reactions occur through self-ionization of the solvent, the concentrations of either the cation or the anion is changed. For example, the solvolytic reactions in water, ammonia, ethanol are given below. Number 1. Water as solvents. 2H2O is in equilibrium state with H2O positive plus OH negative. Number 2. Ammonia as solvent. 2NH3 in equilibrium state with NH4 positive plus NH2 negative. Number 3. Alcohol as solvent. 2C2H5OH in equilibrium state with C2H5OH2 positive plus OC2H5 negative. It may be noticed that in case of solvents like water, ammonia, alcohol, acetic acid, etc., the terms hydrolysis, ammonolysis, alcoholysis, and acetolysis are used respectively. Number 5. Solvation. The reactions in which the molecules of the solvent get attached to a solute species cation, anion or molecule are called solvation reactions. The species formed is called solvent. The solvation reactions in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, etc. The resulting solvates are called hydrates, ammoniates, alcoholates, etc. For example, CuSO4 plus 4NH3 gives CuSO4 4NH3. CuCl2 plus 4H2O gives CuH2O4 whole 2 positive, 2Cl negative. BaSO4 plus 3H2SO4 gives BaSO4 3H2SO4. Solvation of a cation occurs through ion dipole interactions between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecules donate a pair of electrons to the cation. On the other hand, solvation of anions occurs through ion dipole interactions between the negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia, hydrogen fluoride. It may be noticed that in certain cases it is difficult to distinguish between solvation and solvolysis, because in many solvolytic reactions the first steps consist of solvation reactions. However, the term solvation is used for those reactions in which the solvent molecule remain in the resulting product. Let us discuss some reactions into common non-aqueous solvents. Liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvents. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. It is most of the physical properties resembles those of water. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following points. Number 1. Liquid range. The melting and boiling points of the liquid ammonia are lower than those of water. In liquid ammonia, the liquid ranges from minus 77 to minus 33 degrees Celsius, and therefore it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Number 2. Hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strong electronegative element, nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NH bond is weaker than OHO bond. As a result, the freezing point and the boiling point of ammonia are less. Since ammonia is less associated than water, it is better solvent for organic compounds. Dielectric constant. The dielectric constant of ammonia is lower as compared to water, suggesting a lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substances. Soluble salts include most ammonium salts, nitrates, thiocyanates, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia has lower viscosity than water, and this might be expected to promote greater ionic mobilities and thereby compensate to some extent for the effect of dielectric constant. Number 4. Self-ionization. Both ammonia and water show comparable self-ionization as represented below. 2NH3 in equilibrium state, NH4 positive plus NH2 negative. 2H2O in equilibrium state with H3O positive and OH negative. However, the extent of autoionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent than water. The following properties of ammonia make it a better solvent than water. Number 1. Liquid ammonia is a very poor conductor of electricity. Number 2. The specific heat of ammonia is more than that of water. Number 3. Liquid ammonia is less viscous than water. Most salts, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia, but due to low viscosity, which greatly increases the mobility of the ions. Number 4. Liquid ammonia has high critical temperature and pressure. Number 5. It is less associated than water due to lesser hydrogen bonding and therefore is a better solvent for organic compounds. Number 6. Liquid ammonia forms strong reducing metal ammonia solutions with alkali metals. Therefore, it is an excellent solvent for many reduction reactions. Reactions in liquid ammonia. As mentioned earlier, ammonia has water-like properties as a solvent. It is therefore expected that the reactions which take place in aqueous solutions can also occur in ammonia solutions. Some of the important chemical reactions occurring in liquid ammonia are given below. Acid-base reactions. The acid-base reactions in liquid ammonia can be easily understood by comparing the reactions in water to H2O in equilibrium with H3O positive plus OH negative. According to solvent system concept of acid and bases, the substance producing H3O positive ion in a water act as acids while those producing OH negative ions act as base. Liquid ammonia ionizes H2NH3 in equilibrium with NH4 positive plus NH2 negative. Therefore, the substances producing ammonia ions in liquid ammonia behaves as acid while those producing amide ions behaves as bases. For example, ammonia salts such as ammonium halides, thiocyanates, nitrates are soluble in liquid ammonia and behaves as acids. NH4Cl on adding liquid NH3 gives NH4 positive plus Cl negative. Similarly, amides, imides and nitrides behaves as base in liquid NH3, and the commonest base in liquid ammonia is potassium amide KNH2, which ionizes as KNH2 in presence of liquid NH3 gives K positive plus NH2 negative. Liquid amide, sodium amide and alkaline earth metal amide have a very low solubility and therefore KNH2 is the commonest base in liquid NH3. Protolysis. Certain compounds like urea, acetamide, sulfamide, etc., which are incapable of donating protons to water, can readily donate protons to NH3 in liquid ammonia. These reactions are called protolysis reactions, hence these compounds act as acids in liquid ammonia. Acid-base neutralization. In aqueous solutions, the process of neutralization of a strong acid and a base involves the combination of H3O positive and OH negative to form practically unionized water. For example, the neutralization of hydrochloric acid and sodium hydroxide may be expressed as HCl plus NaOH gives NaCl plus H2, or H3O positive plus OH negatives gives 2H2O. In a similar way, the neutralization of an acid and a base in liquid ammonia involves the combination of NH4 positive ion and NH2 negative ion. NH4 Cl plus KNH2 in presence of liquid NH3 gives KCl plus 2NH3, or NH4 positive plus NH2 negative in presence of liquid NH3 gives 2NH3. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acid and bases are called amphoteric substances. For example, in liquid ammonia, zinc amide show amphoteric behavior analogous to that of zinc hydroxide in aqueous solutions. As a base, ZnNH2 twice plus 2NH4Cl in presence of liquid NH3 gives ZnCl2 plus 4NH3. As an acid, ZnNH2 2 plus 2KNH2 in presence of liquid NH3 gives K2ZnNH2 whole 4. Thus, acid gives NH4 positive ions and base gives NH2 negative ions in liquid ammonia. These are termed as amino acids and amino bases. A. Reactions of amino acids. Amino acid is a substance that furnishes NH4 positive ion in liquid ammonia. Ammonia halides, nitrate, thiocyanate are very soluble in liquid ammonia, giving NH4 positive ions, and their concentrated solution act as amino acids. We know that acids give hydrogen with metals in aqueous solution. In a similar way, the amino acids react with alkali and other metals to give hydrogen. 2Na plus 2NH4Cl in presence of liquid NH3 gives 2NaCl 2NH3 plus H2. Mg plus 2NH4Cl in presence of liquid NH3 gives MgCl2 2NH3 plus H2. A saturated solution of ammonium nitrate in ammonia also dissolves many metal oxides similar to their behavior in aqueous acids. Na2O plus 2NH4Cl in presence of liquid NH3 gives 2NaCl plus 2NH3 plus H2O. COO plus 2NH4Cl liquid NH3 gives COCl plus 2NH3 plus H2O. Solutions of ammonium halides in ammonia may be used as acid in the preparation of silane and arsine. Mg2Si plus 4NH4Br in presence of liquid NH3 gives SiH4 plus 2MgBr2 plus 4NH3. Na3As plus 3NH4Br in presence of liquid NH3 gives ASH3 plus 2NaBr plus 3NH3. Reactions of amino bases. Ammonobase is a substance which in liquid ammonia solutions give NH2 negative ion. The commonest base is potassium amide, which is much more soluble than lithium and sodium amides. Metal salts react with ammonobases to give amides, imides and nitrides which get precipitated in liquid ammonia. AgNO3 plus KNH2 in presence of liquid NH3 gives KNO3 plus AgNH2. The precipitation reactions. Precipitation reactions involve double decomposition. Because of the difference in the solubilities of various substances in water and in liquid ammonia, a large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. For example, silver chloride is precipitated in aqueous solution as KCl plus AgNO3 gives AgCl plus KNO3. Similarly, a white precipitate of BaCl2 is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. 2AgCl plus BaNO3 twice in presence of liquid NH3 gives BaCl2 plus 2AgNO3. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. NH4Cl plus LiNO3 in presence of liquid NH3 gives LiCl plus NH4NO3. Number 2. Iodides and bromides get precipitated when solutions of various nitrates and ammonia halides in liquid ammonia are mixed together. ZnNO3 whole twice plus 2NH4I in presence of liquid ammonia gives ZnI2 plus 2NH4NO3. Number 3. Many metal sulfides can be precipitated in liquid ammonia by ammonium sulfides from the nitrate solutions of the metal. NH4 2S plus 2AgNO3 in presence of liquid NH3 gives Ag2S to NH4NO3. NH4 2S plus CuNO3 whole twice in presence of liquid NH3 gives CuS plus 2NH4NO3. NH4 2S plus CdNO3 whole thrice in presence of liquid NH3 gives CdS plus 2NH4NO3. Number 3. Ammonolysis. The solvolysis reactions in liquid ammonia are called ammonolysis or ammonolytic reactions. These are analogous to hydrolysis reactions and involve the attachment of ammonium ion or amide ion to the reactant. For example, hydrolysis of SiCl4 occurs as SiCl4 plus 4H2O gives SiOH4. Similarly, ammonolysis of SiCl4 may be written as SiCl4 plus 8NH3 gives SiNH3 NH2 whole 4 plus 4NH4 positive plus 4Cl negative. It may be noted that in ammonolysis an atom or ion from a substance is replaced by nitrogen containing ion or radical. Some ammonolysis reactions are HgCl2 on adding liquid NH3 gives NH2 HgNH2Cl. CCl4 on adding liquid NH3 gives CnH2 twice, etc. In excess of liquid ammonia, the ammonolysis of TiCl4 occurs in steps as TiCl4 on adding liquid NH3 gives TiCl3NH2. On adding liquid NH3 gives TiCl2NH2 twice. On adding liquid NH3 again gives TiClNH2 thrice. On again adding liquid NH3 gives TiNH2 4. When organic halides which undergo slow ammonolysis are ammonolized at the boiling point of liquid ammonia, mixtures of primary, secondary and tertiary amines are obtained. Rx plus 2NH3 gives RNH2 plus NH4X. Rx plus RNH2 plus NH3 gives R2NH plus NH4X. Rx plus R2NH plus NH3 gives R3N plus NH4X. The ammonia molecules is basic and has strong tendency to accept protons and therefore it will act as base. However, towards very strong bases it acts as proton donor. Examples of type of ammonolysis reactions are NaH plus NH3 gives NaNH2 plus H2. NaCH3 plus NH3 gives NaNH2CH4. Na2O plus 2NH3 gives 2NaNH2 plus H2O. Number 4. Complex formation reactions. Many complex formation reactions in liquid ammonia are reported which are similar to reactions occurring in aqueous system. For example, zinc nitrate reacts with potassium amide to form insoluble zinc amide which dissolves in excess of amide due to formation of complex compound of zinc. ZnNO3 whole twice plus 2 KNH2 on liquid NH3 gives ZnNH3 twice plus 2 KNH3. This reaction is analogous to reactions of zinc nitrate with sodium hydroxide in water. ZnOH twice plus 2 NaOH on adding H2 gives Na2ZnOH4. Some other complex reactions in liquid ammonia are CuCl2 plus 4NH3 on adding liquid NH3 gives CuNH3 4Cl2. Number 5. Formation of ammoniates. Just as water from hydrates, ammonia also forms ammoniates with many inorganic salts. In these compounds, the ammonia molecules are coordinated to the cation. Some typical ammoniates are BF3 plus NH3 on adding liquid NH3 BF3.NH3. Number 6. Redox reactions. Liquid ammonia acts as an excellent medium for redox reactions. In liquid ammonia, the oxidizing action of strong oxidizing agents is weaker than in water solution. For example, HNO3 in liquid ammonia does not act as an oxidizing solvent. Similarly, KMNO4 in liquid ammonia acts as a very weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metals act as very powerful reducing agent in liquid ammonia. For example, sodium salt in liquid ammonia reduces CuI to Cu, KMNO4 to K2MNO4, etc. Solutions in liquid ammonia. Number 7. The dielectric constant of liquid ammonia is low, therefore it is expected to be a poor solvent for ionic substances. Amongst the inorganic compounds, all ammonia salts, nitrates, thiocyanates and iodides are soluble in liquid ammonia. Oxide, hydroxides, carbonates, phosphates, sulfates and most of the sulfides are insoluble. Most fluorides are insoluble in liquid ammonia, and the solubility among halides increases as F negative, then Cl negative, then Br negative and then I negative. Most of the iodides are soluble. Calcium and zinc chlorides, which are extremely soluble in water, are quite insoluble in ammonia. Organic compounds such as halogen compounds, alcohols, ketones, esters, simple ethers, phenols, amine, nitro compounds, etc. are readily soluble in liquid ammonia. Aromatic hydrocarbons are sparingly soluble. Paraffins and benzenes are not soluble. Amongst the elements, metals like Mg, Al, Zn, Ca, La, Ce, Mn, etc. are only slightly soluble in liquid ammonia. Alkali metals and alkaline earth metals are highly soluble in liquid ammonia. These form very interesting solutions and are discussed below. Non-metals like Sp, Sc are soluble in liquid ammonia. Solutions of alkaline metals in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkaline metals. The resulting solutions are blue and extremely good electrical conductors. The important characteristics of alkaline metal solutions are: number 1, these are blue in color and the color is independent of metal dissolved. Number 2, when the concentration of the metal is increased, the color changes to bronze and show metallic appearance. Number 3, these solutions are conducting and show strong reducing properties. Number 4, these solutions are paramagnetic and the paramagnetic character decreases with increasing concentration. Number 5, if the reagent are pure, dry and sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metals are dissolved in liquid ammonia, they ionize to give metal ion and valence electron as Na on adding liquid NH3 in equilibrium with Na positive plus electron negative. The ammoniated electrons are responsible for a blue color of the solution. This is due to the absorption of visible light by ammoniated electrons. The electrical conductance is also due to ammoniated cations and ammoniated electrons. The conductivity of a metal in liquid ammonia is comparable to that of an aqueous solution of a typical ionic compound. As the concentration of the solution is increased, the ammoniated cations and electrons associate, resulting in a decrease of conductivity. Very dilute solution of alkali metals in liquid ammonia are metastable and when catalyzed they undergo decomposition. As the concentration of the metal increases, the blue color changes to bronze and finally the blue color disappears altogether. This is due to the fact that impurities such as iron oxide catalyze the conversion of metal into amide. 2M plus 2NH3 gives 2MnH2 plus H2. On evaporating the alkali metal ammonia solution, alkali metal can be recovered. The strongly reducing character of this solution is due to the presence of readily available electrons. The important applications of alkali metal solutions in organic chemistry is the reduction of many functional groups and unsaturated compounds. As already studied, the liquid ammonia is a thoroughly studied non-aqueous solvent. Some of its advantages and disadvantages as a solvent are given below. Advantages of liquid ammonia as a solvent. Number 1. The dissolution of alkali metals without chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metals can be recovered from the solution by evaporation. Number 2. The alkali metal solution are strongly reducing agents, even stronger than hydrogen. Number 3. Ammonium salt dissolves in liquid ammonia act as amino acid, and these find applications in preparative chemistry. They can be used to prepare silane, arsine, etc. Number 4. The tendency for solvolysis is less in liquid ammonia than in water. Disadvantages of liquid ammonia as a solvent. Number 1. The liquid range for liquid ammonia is from minus 33.3 degree to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessarily while working with liquid ammonia. Number 2. Liquid ammonia has an offensive odor, therefore it requires special techniques to use it as a solvent and as a reaction medium. Number 3. Liquid ammonia is hygroscopic in nature and hence all the reactions are to be carried out in sealed tubes. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the important non-aqueous solvent and has been widely used in industry. Under normal conditions of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and easily maintained in liquid phases. It has a wide liquid range and can be used as solvent. It can be easily purified by passing the gas through sulfur dioxide and through P2O5 to remove traces of water. Its dielectric constant is small and therefore a good solvent for covalent compound. The characteristics, physical properties of liquid sulfur dioxide are given. Structure of sulfur dioxide molecule. Electron diffraction studies have shown that sulfur dioxide in gaseous phase has the angular structure. The valence bond theory predicts that SO2 molecule is a resonance hybrid of the following two resonating structures. Solubility of compounds in liquid sulfur dioxide. Amongst the inorganic compounds, iodides and thiocyanates are most soluble. In case of alkali metals halides, the solubilities are in the order Mi, Mbr, Mcl and then Mf. And this is in decreasing order. The uninegative polyatomic anions such as ClO4 negative, NO3 negative, Bf4 negative, etc. are generally more soluble in liquid SO2. Salts of multi-negative anions such as SO4 negative, SO3 negative, S2 negative, O2 negative are practically insoluble. Many of the ammonium, thallium and mercuric salts are soluble. It is an excellent solvent for covalent compounds. Many covalent compounds like halogens, interhalogens, phosphorus halides, oxyhalides of sulfur, phosphorus, etc. and the halides are soluble in 8 metals are insoluble in liquid SO2. Amongst the organic compounds, aromatic hydrocarbons and alkenes have very high solubility in liquid SO2 in comparison to saturated hydrocarbons. Pyridine, quinoline, ethers, halogen derivatives and acid chlorides also dissolve in liquid SO2. Many compounds dissolve in liquid SO2 due to solvate formation. For example, Ki4SO2, CaI2,4SO2, KSCnSO2. Many donor molecules also form stable solvates with SO2. For example, C5H5nSO2, C6H5OCS3, SO2, BF3SO2, etc. Autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to autoionize H2SO2 is in equilibrium with SO2 positive plus SO3 negative. The thionyl ion is analogous to hydronium ion and ammonium ion, and sulfite ion corresponds to hydroxyl and amide ions in the aqueous and ammonia systems respectively. Reactions in liquid sulfur dioxide. Some important chemical reactions in liquid sulfur dioxide are discussed below. Number 1. Acid-base reactions. Liquid SO2 undergoes autoionization. H2SO2 gives SO2 positive plus SO3 negative. According to solvent system concept of acid and bases, the compound which give thionyl ions in solutions of SO2 would behave as acid, whereas compounds giving sulfite ions in liquid SO2 would act as base. For example, compounds such as SOCl2, SOBr2, etc. act as acids in liquid SO2. On the other hand, cesium sulfide increases the concentration of sulfite ions and therefore behaves as bases. Typical acid-base neutralization reactions in liquid SO2 may be given as SOCl2 plus CS2 SO3 on adding liquid SO2 gives to CSCl plus 2 SO2. Amphoteric behavior is shown by zinc 2 and aluminium 3 ions. For example, AlCl3 reacts with SO3 to negative ions in liquid SO2 to form insoluble aluminum sulfite Al2SO3 whole thrice. However, if the precipitate is treated with the excess of sulfite, the precipitation redissolves. 2AlCl3 plus 3K2SO3 gives Al2SO3 thrice plus 6KCl. This reaction is analogous to behavior of AlOH3 thrice in water. AlCl3 plus 3 NaOH on adding H2O gives AlOH3 plus 3 NaCl. If some acid SOCl2 is added to the soluble complex solution and the aluminium sulfide reprecipitates. This reaction is also analogous to reaction in water. Similarly, salt of zinc 2 show amphoteric behavior in liquid SO2. ZnCl2 plus K2SO4 on adding liquid SO2 gives ZnSO3 plus 2 KCl. Solvolytic reactions. Solvolytic reactions in liquid sulfur dioxides are not as common as they are in other protonic solvents such as NS3. Some reactions are given below. Ammonia acetate is solvolized in liquid SO2. This reaction is analogous to the reactions of ammonium acetate in water. Number 2. Certain covalent halides such as PCl5, PBr5, UCl6, ASCl5, WCl6 undergo solvolysis in liquid SO2 in sealed tubes. PCl5 plus SO2 liquid gives POCl3 plus SOCl2. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, BCl3, SCl2, SCl4, MoCl6, etc. do not undergo solvolysis in liquid sulfur dioxide. The formation of solvent, etc., that is, the addition compounds with the solvents, is also known. Typical examples of solvent are NaI, 4SO2, RBI, 4SO2 KBr, 4SO2 CaI2, 4SO2 BaI2, 4SO2 SRI2, 4SO2, AlCl3 to SO2, etc. Number 3. Precipitation reactions. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubilities of compounds. The precipitation of several insoluble compounds in liquid sulfur dioxide can be carried out by treating them with soluble compounds in sulfur dioxide. Some of these reactions are SbCl3 plus 3 LiI on adding liquid SO2 gives SbI3 plus 3 LiCl. Number 4. Complex formation reactions. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of the complex Ki3 or RbI3. Ki plus I2 on adding liquid SO2 gives Ki3. Similarly, the increase in the solubility of cadmium iodide, mercuric iodide in liquid sulfur dioxide is attributed to the formation of the complexes. AlCl3 reacts with SO3 to negative ions to form a precipitate of Al2SO3 whole thrice, which redissolves in excess of SO3 to negative ions, forming the complex ion AlSO3 thrice whole thrice negative. Number 5. Organic solvents. Organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is relatively inert solvent. Some common examples are: Number 1. Sulfonation of aromatic hydrocarbons by sulfur trioxide or chlorosulfuric acid. C6H6 plus SO3 on adding liquid SO2 gives C6H5SO3H. Number 2. Liquid SO2 has also been used as a solvent for Friedel-Crafts type reactions. In these reactions, AlCl3 is used as a catalyst which is highly soluble in liquid SO2. C6H6 plus TC5H11Cl on adding AlCl3 liquid SO2 gives TC5H11 C6H5 plus HCl. Number 3. It is also used as a solvent for the addition and substitution of bromine reactions. Number 6. Sulfur dioxide of crystallization. These reactions are also called solvation reactions. Like water and ammonia salts having sulfur dioxide of crystallization have also been observed. Some examples are NaI, 4SO2 Ki, 4SO2 Li, Li2SO2, Bi2, 4SO2, AlCl3SO2, KCNSSO2. These are formed with the highly soluble salts, are analogous to hydrates. Number 7. Redox reactions. The gaseous sulfur dioxide behave both as oxidizing and as reducing agent. Liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply acts as a medium for certain redox reactions. For example, iodine is liberated from Ki in the presence of SbCl5 in liquid sulfur dioxide. 6 Ki plus 3 SbCl5 to K3 SbCl6 plus SbCl3 plus 3I2. 2Ki plus 2FeCl3 gives 2FeCl2 plus 2KCl plus I2. Some special features of liquid SO2 act as solvent. Liquid sulfur dioxide possesses some special advantages over other solvent as a reaction medium. Some of these are: number 1, it has low boiling point, and this allows its easy evaporation and therefore removal from the reaction mixture. Number 2, it has low melting point and therefore it allows reactions to be carried out at low temperature. Number 3, liquid SO2 is an inert solvent. Number 4, it has unusual solvating powers for both covalent and electrovalent compounds. Number 5, it is a better medium for covalent compounds like hydrocarbons and is used for the purification of some petroleum products. Number 6, it is used as a diluent for the superacid medium, which helps in reducing its viscosity without affecting its acidity. Thanks.